Superposition changes everything. You are first taught that when you have a compound rod, that if you want to find change in length from A to C, that you can just calculate the change in length from A to B and the change in length from B to C and add those two together, and that's your overall change in length. And that is true. But it's not the only way to solve this type of problem. You can also say that the overall change in length from A to C is the change in length due to force 1 plus the overall change in length due to force 2. So you can split up your compound member based on either sections of the beam or causes of the loading. Different forces get separated. Once I made that connection, then that presented whole new options for how to make problems easier, which is always the goal, to solve the easiest way possible. So for this indeterminate loading problem, I am going to first ignore the bottom ground, ignore that gap. Just look at this 400 kilonewton force, figure out how much it stretches the beam. And it's going to go through the floor, probably. So then separately, I will then figure out how much force would the floor have to be pushing back up with in order to shorten the beam back to the level of the ground. Number one most common mistake on axial loading problems. Tension and compression require a force on both sides. If I want to stretch something, I have to be pulling on both the left and the right. If I want to compress something, I need to push in from both the left and the right. If I take an object and only push it from one side, it's not going to compress. It's just going to move, right? You get compression and tension from being squished or pulled both ends. This 400 kilonewton force, it is going to be pulling section AB in tension, because while the 400 is pushing down, the ceiling at the top is holding it up. So we're pulling the top in tension. But BC, since C is just floating in the air, the 400 is pushing it down and nothing is pushing back up. So BC is just moving downwards. It's not being compressed initially by this 400 kilonewton force. It's just along for the ride. As AB stretches, however much it stretches downwards, BC moves downwards, but doesn't change length. It won't be until later in the problem, when we actually figure out how much force the ground pushes up with, that's when we'll be able to figure out how much it compresses. But that part comes later. By solving each force separately, the 400 is only stretching AB, it's doing nothing to BC. So delta AC is just delta AB for the 400 kilonewton force. I can plug in my numbers, pi r squared for the area, only 0.4 for the length, and I'll have to go down to the tables to look up Young's modulus. I'll grab both the aluminum and steel values because I'm going to need them both eventually. Plug in all the numbers. 1.12 millimeters is how much AB stretches. Since the gap is only 0.5 millimeters, that tells us that yes, the entire gap would get filled, and basically the 400 kilonewton force is trying to push BC through the floor. So, next part of the problem, we're going to have to figure out how much the floor pushes back in order to reduce that stretch to an amount that it exactly equals the size of the gap. And this means a compatibility equation. Whenever you're solving an indeterminate loading problem, this could be in torsion or bending or axial loading, statically indeterminate problems always require a compatibility equation. This is a geometric equation that's just based on lengths and angles. In this case, what we are saying is the 0.5 millimeter gap is going to be equal to the amount of gap caused by the 400 kilonewton force plus the amount of gap caused by the force from the wall. And since the force from the 400 kilonewtons was more than 0.5, this tells us that the change in length due to the wall will be a negative value, that force is going to be pushing upwards in compression to reduce the amount, the overall change in length. So this 0.000615 millimeters is going to be equal to how much section AB shrinks due to the force in the wall, plus the amount that section BC shrinks due to the force from the wall. The 400 kilonewton force only acted to stretch AB, right? BC was just along for the ride. But once that gap has been filled and the ground pushes upwards, now the ground is pushing up and the ceiling is pushing back down. So both AB and BC will be compressed by whatever force is pushing in from the wall. So for AB, this N will be the reaction force on the wall. L is the 400 millimeters. Area is the same pi r squared from before. And E is also the same Young's modulus from before. BC is going to be way more complicated though, because BC is composed of two different materials, right? We have the aluminum in the center and there's an outer steel sleeve around it. These two materials are sharing the force. So whatever value N turns out to be, part of that N is going to be supported by the steel and part of it is going to be supported by the aluminum. So N in this equation, NL over AE, will be different for the steel and the aluminum. But their change in length is the same because they're attached to each other. So this lets me write out another compatibility equation. NL over AE for the aluminum is equal to NL over AE for the steel. These are both 0.8 meters long. They're pi r squared for the aluminum, pi r squared outer radius minus the inner radius squared for the steel sleeve, like the ring. Plug in the two different values for Young's modulus E. In the numerator, I'm calling N aluminum the amount of force held by the aluminum, which means that the steel is N minus N aluminum. N being the total force from the wall minus N aluminum. So if the force from the wall is 100 kilonewtons and the aluminum is holding 10, then the steel is holding the other 90. That's how this is going to work. But let's not lose track of the overall final answer we're looking for. We're looking for capital N, the force from the wall, the reaction force that's in the purple equation. We don't care how much is split up aluminum versus steel. So the way we're actually going to solve this problem is by solving for NaL, rearranging this black equation to solve for NaL, and then plug that in to the purple equation because the NL over AE in section BC is only actually the force in the aluminum section, right? Because both aluminum and steel have the same change in length. So we plug in some numbers, do a bunch of algebra. I'm sorry for the million zeros in all of these. I don't like using scientific notation. It's just a personal preference. I get that the aluminum is holding 0.1017 N. It's holding 10% of the weight, right? The steel is holding 90%. So plugging back into the purple equation, the left side is for section AB. That's the 400 millimeter section at the top, plus NL over AE for BC. That is the 800 millimeter section down at the bottom. I don't need to include both the aluminum and the steel here, right? They are both changing the same amount. I can include either one that I want. Since I already rearranged and solved for NaL, right, this is going to be the aluminum section. So when I plug in numbers here, this 0.1017 N, this means, again, if there's 100 kilonewtons from the wall, then the aluminum is only holding about 10.17 kilonewtons. And so this 0.1017 N represents the force that is stretching the aluminum. We could have oppositely done 0.9 N and then used the Young's modulus for steel and the cross-sectional area for steel in the denominator. We would get the same answer. But with 0.017N, I'm using the area of aluminum, Young's modulus for aluminum. So I plug in a bunch of numbers, 183 kilonewtons for N, the reaction force from the ground. But then I looked at my work and saw that in one of my intermediate steps, I only kept one decimal place, this 0.00006. And I had a feeling that that might actually be messing up my answer. So here in red, you can see where I went through and actually recalculated keeping more decimal places. You should always keep a bunch of extra decimal places for intermediate steps and only do your rounding at the end. So if you actually carry forward and keep the extra digits, I'm actually going to get a final answer of 181 kilonewtons. So you can see the rounding early. It didn't mess up my answer by a lot, but it was noticeable. It was a couple percent different. On all that work, you'd think that we were done, but no, we were asked to solve for the reaction forces. Well, there's two reaction forces. There's the ground, there's also the ceiling. So we still have to do actually a sum of forces in the y direction, 400 pointing down, 181 pointing up, which means that the force from the ceiling is actually going to be holding the other 219 kilonewtons, so that the ground and the ceiling together add up to 400. Full mechanics materials playlist is linked down in the description. Go ahead and bookmark it for later. Good luck on your next test.